Hey there folks, this is Mr. Young, and this is my second recorded live lesson for the Polarity unit, Unit 9. In live lesson number 1, I taught you how to analyze a bond and figure out if a bond in a molecule is polar or nonpolar. Now, we're going to analyze a whole molecule and tell if it's polar or nonpolar, and that's going to tell us how molecules can interact with other molecules. We'll really get into IMFs, okay? See here. Okay, so this live lesson is going to help you with box 4 and box 5 of the Polarity Hyperdoc. All right, and then it also will get to box 6 and box 7. We're going to start with molecular polarity. So here's what you already know. Okay, you know how to analyze a bond and tell whether it's covalent. Okay, a covalent bond. Well, right away you know. Oh, well, if you've got a metal and a non-metal, then you've got a ionic bond. Covalent bonds can be polar or they can be non-polar. Okay? Eventually, we're going to use these ideas to analyze a whole molecule and how molecules interact with each other. Just a reminder, just to make sure you're at the right place. Okay, let's analyze some bonds. First up, in this molecule of NH3, okay, this bond right here between the nitrogen and the hydrogen, that is a polar covalent bond because the nitrogen has a high electronegativity, hydrogen has a low electronegativity. So this molecule has 3 different polar covalent bonds. These bonds are all polar bonds and they are covalent bonds. The CF4 also has polar covalent bonds. Fluorine has a high electronegativity, carbon has a low electronegativity, so all these bonds are polar covalent bonds. But now if we look at the O2, that has one bond, a double bond. Okay? It's a non-polar covalent bond because the electrons are being shared equally between these 2 oxygens. They're the same element, they have the same electronegativity. Okay? So that's just a reminder, when you're analyzing a bond, you're looking at just one part of a molecule that may have multiple bonds. And now we're going to look at the whole molecule. Okay, when we analyze a whole molecule, and when we're doing this, we're talking about only covalent molecules. Okay, focusing on covalent molecules here. Forget about ionic for now. When we analyze the whole molecule, we're wondering about how are the electrons distributed overall through the whole molecule. What kind of symmetry does it have overall? Are the electrons distributed equally or unequally? Is it lopsided or not? So a polar molecule will have a lopsided distribution of electrons. Okay. Now, we said that this NH3 has polar bonds. The CF4 has polar bonds. The oxygen has nonpolar bonds. Now let's look at the whole molecule. Okay. In the NH3, nitrogen has a high electronegativity. Hydrogen has a low electronegativity. So we can draw what we call a dipole. This arrow is a dipole. It's positive at one end. See the little plus sign here, okay? And then it points towards the negative end. The nitrogen has a high electronegativity. It hogs the electrons. You can even see there are 2 extra electrons here. This is definitely the negative end of this molecule. So a dipole is this arrow we can draw on a molecule that points towards the negative end of the molecule. Since this molecule has a negative end, it is lopsided. This is a polar molecule. Okay? The electrons are distributed in an uneven way. The electrons are more close to the nitrogen. We've got these extra electrons here. Nitrogen pulls the electrons in the bonds towards itself. It's a lopsided molecule. Now let's look at this CF4. CF4, it has a bunch of polar bonds, but here's the special thing. Oh, you know what? Let's analyze oxygen first. Okay, Mr. Young, get with it. Those are 2 atoms of oxygen bonded together. They both have the exact same electronegativity. It's a nonpolar molecule because the electrons are distributed evenly overall. The 2 oxygens share their electrons with each other equally. They have equal electronegativities. Okay, now let's analyze the CF4. This is the interesting one. It's made of polar bonds. Okay, carbon has a low electronegativity. Each fluorine has a high electronegativity. And the fluorines have all these electrons around them. What that means is the fluorines are all negative and the carbon is kind of positive. We could draw 4 different dipoles where it's negative towards the fluorine, negative towards the fluorine, negative towards the fluorine, negative towards the fluorine. All those four dipoles cancel each other out, up and down and side to side. So overall, this is a non-polar molecule. Remember, a polar molecule means the electrons are distributed in a lopsided way. In CF4, the electrons are distributed evenly around the whole molecule. Okay, so it's a non-polar molecule. You can also think of this in terms of symmetry or folding. Okay, let's talk about how you do that. All right. So when analyzing the whole molecule, you can think about electron distribution, look for the electrons, or you can think about folding and symmetry. Okay. If we draw that CF4 on a piece of paper, we could fold it horizontally. It will be the same on either side of the fold. We could fold it vertically, and we will have the same thing on either side of the fold. We could fold it diagonally, either way, and it will be the same on either side of the fold. That means we have multiple axes of symmetry. If there's more than one axis of symmetry, it's a non-polar molecule. That means it's symmetrical in many different directions, or more than just one direction. Let's look at NH3. Okay, and again, CF4 is a non-polar molecule because it has multiple axes of symmetry. NH3, if we draw that on paper, there's only one way to fold it, where it will be the same on either side. If we fold it vertically, it'll be the same on either side. If we fold it horizontally or diagonally, we will not get the same thing on either side of our fold. This has only one axis of symmetry. That means it is lopsided. It is a polar molecule. If it only has one axis of symmetry, it's going to be a polar molecule. O2. O2. Imagine that you draw an axis of symmetry vertically and horizontally. The O2 will be the same on either side of the vertical axis, same on either side of the horizontal axis. It has more than one axis of symmetry, so it is a non-polar molecule. Okay? So you can look at how the electrons are distributed, or you can think about symmetry. One axis of symmetry means polar. Let's go through a few examples. Is it polar or is it non-polar? I know you guys love this one. All right, Cl2. Is it a polar molecule or a non-polar molecule? Okay. Look at where the electrons are. Think about the symmetry. You can think about it either way. Okay, Cl2 is a non-polar molecule. Here's how I would analyze it. I would say, oh, two chlorines, same electronegativity. They're sharing their electrons equally. I see a bunch of electrons around each chlorine. So the electrons are equally shared and equally distributed through this molecule. You could also say, oh, I can draw two different axes of symmetry. It has more than one axis of symmetry, so that means it's a non-polar molecule. Excuse me. Let's try another one. And remember, non-polar molecules have electrons distributed equally. Polar molecules have a lopsided distribution of electrons. HCl, look at the electrons, think of the symmetry. Is it a polar molecule or a non-polar molecule? HCl is a polar molecule. Here's how you could analyze it. The H and Cl, there's only one bond there, and the chlorine has a very high electronegativity, hydrogen kind of a lower electronegativity. So it's a lopsided situation. You could draw a dipole. You could say, oh, it's kind of positive at the hydrogen end, kind of negative at the chlorine end, partly because the chlorine has high electronegativity, and the chlorine has all those electrons around it. You could also draw one axis of symmetry. You can't draw another axis of symmetry. There's only one way to fold this to get the same thing on either side of the fold. So it has an asymmetrical shape and asymmetrical distribution of electrons. It is a polar molecule. And all these ways of thinking about this are valid. You can use whichever one makes more sense to your brain to figure out if a molecule is polar or non-polar. I'm going to do a couple more examples. Okay. CO2, carbon dioxide, is it polar or non-polar? Look at where the electrons are. Look for axes of symmetry. It's a non-polar molecule. Okay, we've got the carbon in the middle with a low electronegativity, oxygen on either side with a higher electronegativity. That means it's got a dipole in each direction. It's got those electrons on the oxygens on either end. So that makes it have a symmetrical distribution of charge or symmetrical distribution of electrons. Or you could say, oh, I could draw a horizontal axis of symmetry, and I can draw a vertical axis of symmetry. If I fold it either way, it will be the same on either side. That means it has more than one axis of symmetry. It is a symmetrical molecule, symmetrical shape, symmetrical distribution of electrons. CH4, methane. CH4, is it polar or nonpolar? Look for electrons, look for axes of symmetry. And this one looks pretty symmetrical. It is. Yes, the carbon has a higher electronegativity, but the hydrogens in 4 directions has a lower electronegativity. That means you've got 4 dipoles going inward towards the carbon. They balance each other out. Or you can say, oh, I could fold this horizontally, fold it vertically, fold it diagonal in either direction. It's got multiple axes of symmetry. That means it's a non-polar molecule. It has a symmetrical shape and distribution of electrons. It's not lopsided. Finally, what would this be? This would be fluoromethane. Okay, it's like methane, but then one of the hydrogens is replaced with a fluorine that has all those extra valence electrons. Is it polar or nonpolar? It doesn't seem symmetrical. It's polar. Okay, the fluorine has a very high electronegativity compared to the carbon and the hydrogens. The electrons are being pulled towards the carbon and very heavily towards the fluorine. And the fluorine has all those extra electrons around it. So we've got a dipole that goes towards the fluorine, kind of through the molecule. It is a lopsided molecule. You could also think, oh, I can only draw one axis of symmetry, and then it'll be the same on either side. If I try to draw a vertical axis of symmetry, it wouldn't be the same on either side. So with only one axis of symmetry, this is a polar molecule. It has an asymmetrical shape and distribution of electrons. It is lopsided. Okay, I want you to look at this molecule. This is carbon tetrachloride. Carbon in the middle, 4 chlorines around it. And this is kind of an interesting situation. So look at it carefully and listen to my voice. Okay, overall, this is a non-polar molecule. It's got an even distribution of electrons in 4 directions. But it's made up of polar bonds. So here we have a situation of a non-polar molecule that has polar bonds inside it. Now you may be saying, big deal, but this will trip you up later, okay? You can have something that has polar bonds, but overall it's a non-polar molecule. When you're reading about things like this, you have to be careful. Are they using the word polar to talk about a bond, or are they using the word polar or non-polar to talk about the whole molecule? So be careful. Are you thinking about a bond being polar or non-polar, or are you thinking about a molecule being polar or non-polar? So you can have a non-polar molecule that's made up of polar bonds if they all balance each other